What we now want to look at are limiting factors. This is a part of decision making. And what we're talking about here is that we have a limiting factor or constraint, something that limits the level of activity of the business. Now, normally the limiting factor would be sales demand. But what we're focusing on here is where the limiting factor is something other than sales demand. So the sort of examples we may have, well, I suppose you could guess they are going to be all the factors of production. For example, we may have a limited amount of material, or we may have a limited amount of labour hours, or alternatively, possibly machine hours. Given that we have this limitation, it is critical to maximise profit in relation to that limitation. We're going to see two examples of this. You see, one thing we're going to look at is something called the limiting factor decision. And this is really quite straightforward. The key about the limiting factor decision is that there is only a single limitation or a single constraint. Secondly, we have the joy of looking at linear programming. And when we look at linear programming, what we're seeing is something slightly more complex, where we have multiple constraints. So let's start with the limiting factor decision. Very straightforward, I hope, but let's make sure we can run it through. Our aim is very straightforward. Given that we're looking at a level of activity, fixed costs are not relevant. So the key thing that we're aiming to do is to maximise contribution. Remember, we have a limited resource, something such as material available or labour hours. In order to maximise contribution overall, what we must do is maximise contribution in relation to those units, per unit of scarce resource, or, if you wish, per unit of limiting factor. That being the case, let's look at a silly question. All I've got here are two products. We're looking at two products with differing selling prices and variable costs. We have the contribution per unit, but remember, this is the contribution per unit of sale. And what we want is the contribution in relation to the limiting factor. All I would want to do is to look at the individual products, R and S, take the contribution per unit, (8) and 12. Oh, if we stop there for a second, it looks like S is better than R. And if we just based it on contribution per unit, we would choose a unit of S over a unit of R. Remember, what we're trying to do here is to relate the contribution to the limiting factor. If the limiting factor is the number of machine hours, we have our machine hours per unit, 1 for R and 2.5 for S. By dividing through by the machine hours per unit, we end up with the contribution per unit of machine hour. 8 divided by 1, I can just about do that, 8. 12 divided by 2.5, something like 4.8. once we've related the contribution to the scarce resource or limiting factor, we now notice that S does not earn as much contribution as R, not in relation to the thing that is limited. What we would do next is prepare a ranking. We would rank R1 and S2. Now, of course, you could say that the ranking is not necessary here because there are only 2 products. But in your exam question, you could get 3 or 4 or possibly even 5 products. And the ranking simply makes life that much easier. If we now go back to the question, we can look at further information. We are given budgeted units, 6,000 and 4,000, and we're also given the available machine hours. So not only have we decided that R is better than S, but what we're now able to do is to prepare some form of production schedule to decide how many units of R and S will be produced, and very importantly, given that we've got that far, we could then go further to calculate some sort of total or maximum contribution that we may calculate. If we are looking at our production schedule, on the left-hand side, let's have the limitation, the machine hours. In the middle, the schedule itself, and on the right-hand side, we could always have a place for contribution. Remember, as always, be careful to read the question. Make sure you're answering the question as set and not just calculating numbers for the fun of it. We said we had 10,000 machine hours. Ranked number 1 in the world was product R. How many units of product R did we wish to produce? Well, I think if you look back at the question, we wish to produce 6,000. Are we able to produce 6,000 with the limitation, the number of machine hours? Well, we know that each unit of R requires 1 machine hour. 6,000 multiplied by 1, yes, we can do it. So we will produce 6,000 units of product R. Multiplied by 1 hour per unit gives us 6,000 hours used up, leaving 4,000 left over. Given that we've exhausted the number of units of product R that we can produce, let's go ahead and look at product S. How many units of S can we produce? Well, we wanted to produce more than we are able to because we only have 4 machine hours. And in that circumstance, instead of working from the units to the hours, let's work the other way. If we use up the 4,000 remaining hours, couldn't we say that each and every unit requires 2.5 hours? If that's the case, I think we can produce 1,600 units of product S. So, our production schedule, to maximise contribution and hence profit, we must produce a mix of 6,000 R, 1,600 S. Going further, what was the contribution of R and S? Well, I suppose we're looking at the contribution per unit. And given that we have the contribution per unit, we multiply R by £8 and S by £12. We end up with £48,000 relating to R and 19,200 relating to S. A total of 67,200. Those are the sort of things that you have to do. I think that we're all quite happy with this, because when you look at limiting factor, there are not too many things for you to have to do. Let's just go back through it to remind ourselves of the steps. Remember, our aim, because we wish to maximise contribution, if we have a limiting factor, we will relate the contribution to that limiting factor. To do that, what we have done, we've taken our contribution per unit, we've divided through by the scarce resource or limiting factor per unit, here the machine hours. That gives us the contribution measure that we need. Once we have those values, we are able to rank, and then finally we would use up the machine hours in order of the ranking. I don't think this is too difficult. You're always going to get at least one limiting factor question. Now let's take things a little bit further. We want to look at something called linear programming. Now, we've already discussed the issue. It is closely related to the limiting factor idea that we've already talked about. But the issue with linear programming is that we have multiple outputs. You know, in the example we've just seen, the outputs would be the products R and S. We also have multiple constraints. Well, the example we've just looked at, the constraint was the machine hours. Well, if we have two or more outputs and two or more constraints, things become that much more awkward. You see, before, all we had to do was to make sure that we got as much contribution as possible in relation to machine hours. If we were to have a second constraint, we may find that the relationship differs. Linear programming allows us to get the best mix, no matter how many constraints there are. The best thing to do would be to use the question that we already know and love, where we have products R and S and already have a constraint with regard to machine hours. All we're going to do is to introduce a second constraint on the basis that if we introduce a second one, we have a linear programming environment, and from that we are then able to learn the rules of how we deal with it. So going back to the question we had before, we'll now make the available machine hours 12,000. But just to add a little bit of fun, instead of just having the machine hour constraint, we will now have a labour hour constraint as well. The labour hours per unit are 3 hours per unit for R and 2 for S. And the total amount of labour hours available are 20,000. Okay, so we have all the constituent pieces of information. We know that our output are R and S. We may start talking about them as output variables, if you wish. Our inputs are machine hours and labour hours. And what we want to do is to generate as many outputs of R and S as possible in order that we can maximise contribution. That being the case, what we need to do is to break linear programming down into some very simple steps. Remember, each of these individual steps are the things that your examiner is likely to examine. Step 1. First of all, we have to define our variables. It's not a big issue, this, but it's very important that we get into good habits. Secondly, we identify what we're trying to achieve, the objective function. I think you and I know that in most of these sort of questions we'll be looking to either maximise contribution or just possibly minimise cost. Then we can look at the constraints, the things that limit us from doing what we want to do. 4, we will need to graph the information. That means to illustrate the information graphically that allows us to make a decision. And 5, once we've done that, we then aim for the optimal solution. So let's start by defining the variables. When we define the variables, all we do is this. We want to make sure that R and S relate to an axis on each axis on a graph. If you wish, let one unit of product R equals X, and let one unit of product S equal Y. It doesn't matter which way round you put them. If you put them the other way round, you will simply get a mirror image. It will still give you the same result. One other thing we may wish to define. We know that we're looking at contribution here. And given that we're looking at contribution, the only thing we have to focus on is our aim. Let Z equal maximum contribution. We could use any nomenclature whatsoever, but Z is quite commonly used in this case. So we've defined the variables first of all. Now we can look at the objective function. Well, what is our objective? I think we already know. The objective here is to maximise contribution. And all we're saying is this is what the relationship will be. The maximum contribution is Z. And that is going to be a mix of X and Y. How much does one unit of X earn in contribution terms? If you remember, we earned £8 for every unit of X. And how much contribution for every unit of Y? I think it was £12. So, we have a relationship of X to Y and our overall aim. Once we've got that, we can then look at the constraints, the limits, the things that stop us from producing more than a certain amount. Our first constraint relates to machine hours. If you notice, the maximum amount of machine hours were 12,000. And what we want to do is to understand how much is used in relation to X and how much is used in relation to Y. So if we go back to the question, we see that we use 1 machine hour on every unit of X, sorry, R in the original example, and 2.5 for every unit of S, now Y. So all we do is, again, set up a statistical relationship between one and the other. I could write 1x, but x is absolutely fine, plus 2.5y. Well, it's a constraint. We know that the mix of x and y must be less than or equal to the overall maximum. So, help me with the second one. We know we have a constraint with regard to our labour hours. If we go back to the question, what we see this time is that we have 3 hours and 2 hours for X and Y, and the total amount available are 20,000. Well, okay, how does that pan out? We're looking at our mix of X and Y. What did we say? We said 3 hours were required for each unit of X and 2 hours for each unit of Y, and they must be less than or equal to 20,000. So we've managed to prepare 2 of the constraints. The only other constraints here are what we would describe as the non-negativity constraints. If you think about it, you can't have negative units of X and Y, so X and Y must be greater than or equal to 0. So, what we want to do is now plot this information on a graph. Please remember, the graph will already be provided for you. You do not need to plot this. At the same stage, by seeing how it is done, maybe you will better understand what it is that we have on the graph. If we take our first constraint, X plus 2.5Y is less than or equal to 12,000. When we plot, we are going to plot the extreme of this relationship. So what we're effectively saying is that the left-hand side and the right-hand side equate. All of the 12,000 hours are used. Once we've plotted the line, then we can establish what that line means. We need 2 points to plot a straight line. If we were to make X equal to 0, we could then establish what Y was. If we were to make Y equal to 0, we can then establish what X is. If we make X equal to 0, effectively, we are saying 2.5y equals 12,000. If we divide 12,000 by 2.5, what do we get? I think we get 4,800. Tell me if I'm wrong. If we are going to make y equal to 0, shouldn't be too difficult, x will then equal 12,000. I can just about do the maths associated with that. X will equal 2,000. We could plot these two values on the graph. Before we do that, let's look at the next constraint. We said 3x plus 2y is less than or equal to 20,000. Think it through. We make x equal to 0, what will y equal? If we make y equal to 0, what will x equal? Well, okay. If we make x equal to 0, 2y equals 20,000. I'm pretty sure that that means that y would equal 10,000. Work the other way and say, well, hold on a moment. If we now make y equal to 0, what must x equal? And I think we find that x has to equal a slightly awkward number, 6667 to round. So we have the two constraints. We've been able to plot them. In a moment we will come back and look at the objective function. But before we do so, let's just go away and plot these on a graph. Okay, now we've got the information plotted on the graph. What does it mean? Well, first of all, just to check that you trust me, we've plotted 4,800y to 12,000x. That was the machine hour constraint. And we plotted 6,667, approximately, x to 10,000y. That's the labour hours constraint. Now, when we look at the machine hours constraint, what does it mean? Well, I suppose what it means is this. We are able to operate at anywhere below this line. Because it is a less than constraint, we can operate anywhere below and to the left of this line. Anywhere up here, however, is not acceptable. If we were to look at the labour hours constraint, again it is a less than constraint. Therefore, we can operate anywhere below and to the left of the labour hours constraint. This means that we can identify the feasible region. The feasible region is that region that is limited by both of these constraints. And I think we're all quite happy that the feasible region would be between corners 1, 2, 3 and 4. We can't be to the left of 1 or below 1 because of the non-negativity constraints. We cannot be above 2 because of the machine hour constraint. We cannot be to the right of 4 because of the labour hour constraint, and we cannot push any further out from 3 because of both the labour and the machine hour constraints. This area is described as the feasible region. Now, we know that the optimal solution will be somewhere in this region. And it won't surprise you to know that the optimal solution is going to be at the edges rather than somewhere in the middle. We would expect the optimal solution to be at an extreme value. Because of the linear or straight line relationship within linear programming, another thing we can say is that the optimal solution must be at one of the corners. 1 or 2 or 3 or 4. And I think we can immediately discount 1 because we would earn no contribution at 0, 0 coordinates. So we've already narrowed down our answer to knowing that the optimal solution will be at one of these 3 points. And the key is how we identify that optimal solution. One thing that the examiner may give you is something called an ISO contribution line. Let's go away and talk about it. Now, an ISO contribution line is simply a line of equal contribution. You see, if you remember back to our objective function, we said z equals 8x plus 12y. What we want to do is we want to find the appropriate mix of x and y. But this ISO contribution line simply reflects the idea that there are a whole host of points, mixes of x and y, that would give the same contribution. What we really need to do is to plot something similar to that which we have done before. If we were just to make a value for z, and we have to make it up. There's no other way around it. Maybe what we could say is z equals 20,000. If z equals 20,000 and I made x equal to 0, what would y equal? Or if I made y equal to 0, what would x equal? Well, okay, if we make x equal to 0, 12y will equal z. If that's the case, couldn't we say that we would need 1,667y? If we make y equal to 0, 8x equals 20,000. What's that? 2,500. So all we're doing here is plotting a line of equal contribution. Once we've got it in place, we can then better talk about it. Let's go back to the graph. Okay, so we've managed to plot our ISO contribution line just here. Now, what is so important about this? Because all I've said is that this is the ISO contribution line if we have a certain value of contribution, in our case 20,000. Well, the fact is that we could write as many ISO contribution lines as we wanted to. If I were just to sketch this for a moment, if I were to double the contribution, the ISO contribution line would look something like that. And triple the contribution, it would look something like that. The quality of the ISO contribution line that we find so important is that the gradient remains constant, regardless of the size of the contribution. If the gradient remains constant, we are now able to understand the point at which we will earn maximum contribution. You see, what we could do is just push out our ISO contribution line. Of course, the line would be longer than this, but the gradient helps us to understand what's happening. You see, the maximum contribution that we can get down here will be at this point. Whereas if we move to point 3, I think we can all see that we earn more contribution. This happens to be the point at which the ISO contribution line leaves the feasible region. That must suggest that we have maximized contribution at this point. So I hope you've managed to understand and appreciate here how this works. If we have an ISO contribution line, and let's take it back to the beginning. The gradient of the ISO contribution line allows us to push out the ISO contribution line until it leaves the feasible region. As we push it out here, we would find it leaves at point 3. And because it leaves at that point, we know that we're maximizing contribution. The only problem we have now is this. How many units are there at point 3? You see, you could maybe just about guess that we've got 3,000 of y. What do you think? And maybe just about guess we've got somewhere near 4,500 of x. But I think we can appreciate that what I'm doing here is never very accurate. So how are we going to understand the coordinates relating to the meeting of these two constraints? Well, maybe some of you remember back to the good old days when you learnt something called simultaneous equations. Now we know that the maximum contribution is earned where labour and machine hour constraints meet. All we have to do is to solve them simultaneously to find that point. Thinking back to our constraints, we had our machine hour constraint, x plus 2.5y, and remember the line equates to 12,000. And we have the labour hour constraint, 3x plus 2y equals 20,000. Well, if you remember, the way we deal with simultaneous equations is that we try to equate one of the variables in order that we are able to eliminate it. And if we have a single variable, we can then identify its value. If we call this Formula 1 and this one Formula 2, my thoughts are this. If we multiply this value by 3, it will equate to this value here. What do you think? I think it will work. Of course, there are lots of different ways of doing this, and I'm sure your maths is better than mine. So Formula 3, we're taking Formula 1 and multiplying by 3. X multiplied by 3 gives us 3x. 2.5y multiplied by 3 gives us 7.5y. And 12,000 multiplied by 3 comes to 36,000. Great. Now we have x as the same value in both formulae, formulae 2 and 3. My thoughts for formula 4 is I'm simply going to say, can't we take formula 3 and from that minus formula 2? Doesn't really matter, but that way we make sure that everything's positive. Not that that's going to hurt you. 3x minus 3 gives you nil. Fantastic. 7.5y minus 2y gives us 5.5y. And 36,000 minus 20,000 gives us 16,000. Not bad. Therefore, y will equal 16,000 divided through by 5.5. I don't know if you remember, but we said that we were pretty sure it was 3,000 units. Is that the case? I don't think so. Well, okay, if we do the calculation, we end up with 2,909 units. Very awkward. But remember, this could easily happen in the exam. Once we've got a value for y, can't we just pump that back into any formula we like? I don't know. If we pump it back into formula 1, what do we say? We say x plus 2.5 multiplied by 2,909 equals 12,000. Oh, this is going to come out rather nicely indeed. So what do we get? Well, if we take the left-hand side from the right-hand side, I believe we end up with x being equal to 4727 units. Pig awful numbers. You would never have got anywhere near these by reading from a graph. Please remember, your examiner does expect you to be able to do simultaneous equations. One final thing before we leave linear programming. Remember what our aim was. Our aim was to establish a maximum contribution. So let's find what that contribution is. We said that the optimal solution is 4727 units of x. And each unit of x earns £8. And it was 2,909 of y. And each unit of y earns £12. The overall contribution is 72,724. And that is the maximum amount of contribution that you may earn. So, what will the examiner ask you here? Well, of course, you're not going to get a large linear programming question. But interpretation of the graph is a classic question that your examiner asks. A little bit of simultaneous equations, maybe. Or a brief interpretation of constraints or an objective function. Looking back at the graph, my thoughts are that the examiner often gives you some sort of ISO contribution line, and given that you have an ISO contribution line, you have to identify the optimal solution. I don't think that's too difficult. Make sure you're able to do it.